All right, welcome back to Origin Seminar. Today we have Feng Long. She's an SMA fellow at Harvard-Smithsonian Center for Astrophysics. This is the third year as a fellow, and she obtained a PhD in 2019 at Kavli Institute for Astronomy and Astrophysics of Peking University. You work with Greg Hertzak, and now I believe that you're also collaborating with Ilaria Pascucci here. Hope I can see you in person. All right, so she's interested in starting planet formation. In particular, I think today we're going to hear about some wonderful thing about protoplanetary disk in Taurus in radio. So she deals with ALMA, obviously SMA and VLA, and those radio data and interesting science. So let's welcome Feng. And Feng, floor is yours.
Thank you, Serena, for the introduction and invitation. It's very happy to see so many familiar faces. I hope we can see you guys in person because I'm in Tucson. So today I'm going to give an overview of our ALMA-Taurus survey that many of you might know. And so this involves a large team effort, including many UA collaborators, including like people from Ilara's group, and of course, Paula Pinina, who was a postdoc here at UA. Then I will provide some updates from my recent work on this topic. Okay, so by far we have found so many exoplanets, and the most interesting part is that we see a huge diversity in those planetary architectures. This rich diversity must have its origin, which is inevitably linked to their birth environments, the gas-rich and dusty protoplanetary disks. So when planets form in disks, they imprint signatures on the density temperature structures of disks. And those signatures therefore become the best tools that we can use to study the young hidden planets and also to understand the earliest phase of planet formation. Of course, to study the signatures, class 2 disk stage is the best chance that we could do because at this point, the massive envelope has been largely dissipated, then we can directly observe the disks. So let me try to first give you a simple sketch of how a disk structure would look like. And this gives an adjunct view of how a disk with different components might distribute. So disks is composed of gas parcels and dust grains of different sizes. While the gas particles will fill in all area of the disk, the distribution of dust grains will highly depend on its size. So the smaller the grains, the stronger coupling between the dust grain and the gas. So the similar distribution and dynamics will be there. So that being said, the smaller grains can appear high in the disk atmosphere. But when smaller grains stick together, they will grow to larger size. Those heavier, larger grains will settle towards the disk midplane. So this kind of layer structure can be proved by different disk observables. So here I'm showing using tetrahedra as an example. The 3 panels are showing at the same physical scale. So you can see that the near-infrared scattered image can prove the small micron-sized grains that can appear high in the disk surface, and they have very similar radial extension to the molecular gas emission that usually prove the cold gas disk, like common CO, trace of CO. However, for the thermal continuum emission at millimeter-centimeter wavelengths, usually provided by ALMA or VLA, that we are looking at those large pebbles in the midplane. So this high-density midplane is the optimal places for planet formation to occur because it's high density, and this will be the focus of my talk today. As you can see that apparently there's a difference in their distribution. We see that the large pebble distribution is in a much more confined region compared to those gas distribution and the small micron size. This involves a process we call as radial drift. So to put this simply, so you can imagine a disk with a smooth disk that has high temperature, high density in the central region. So the pressure force will point outwards. So the gas will be affected by this pressure gradient. They will move slightly slower than the free-floating large dust grains. So this velocity difference will introduce a gas drag on the larger grains, and they will be pushed inward to the higher pressure region. So this can explain the difference view of their sizes. However, there's a problem with this process that by theoretical calculations, the radial drift is always too efficient that they remove dust grains too quickly in outer disk. And so if based on that calculation, we shouldn't be able to see so many large disks. And therefore, a natural explanation for these small sizes or this larger grain distribution would be to invoke local pressure perturbations to the gas surface density that can control the radial drift efficiency. So I'm trying to show two simulation examples, see how we can understand this process better. So here is showing by some simulation conducted by Paula Pinilla, and he did two examples, one without pressure gradient without local pressure bumps, another one they add a few. So in the left-hand side, the plots in x-axis show the disk radius, and the y-axis show the grain sizes. And the color scale gives us a handle on the density of the dust grains. So the lighter color means higher density. So in the case of no pressure bumps, the larger grains will only populate in the inner disk due to the radial drift. However, if we can add some local pressure bumps in the system, and the larger grains will accumulate around the pressure peaks, and then we can sustain a larger disk. And so there are many mechanisms to produce these pressure bumps in disks. Of course, planets will be the most exciting possibility, but there are also many others. And this is one hot topic in the field, trying to understand how to make those pressure gradients. But in any case, if you can make a synthetic image based on those simulations, you see many ring-like features. This is like a face-on view of a disk. And those features are exactly what we just observed. So those observational evidence of ring-like structures are the main driver of the field of disk observations. The D-sharp ALMA large program is, of course, a great example. So this large program have targeted 20 bright disks and selected from different star-forming regions. They try to look for the fine details of dust distribution. So what they found is that every disk is highly structured, though their morphology can be quite diverse. So in those systems, somehow some mechanism can work to create pressure bumps maybe, and then track larger grains forming a ring-like structure. So understanding the formation evolution of those substructures will be the new frontier of our studies. However, this will require a larger sample analysis and also involves different disk tracers to be combined to answer that question. So today in this talk, this is a brief outline. I'm going to first give some overview on our ALMA Cycle 4 Taurus survey with high resolution for 32 disks. Then I will move to a larger view that in Taurus by combining many archival data together. At the end, I will try to show how, for example, how we can use those binary disk interactions models and to try to understand what the perturber can do for the disk structure. So a few years ago, we have conducted this ALMA survey trying to look for 32 disks in Taurus at 0.1 arcsecond resolution, which targeted 1.3 millimeter continuous emission and 2 CO lines. The main goal of this program was to establish an initial assessment on how the disk structure looks like at 10 to 20 AU scale. So our main And sample selection criterion is based on the spectral type. We only select earlier type stars, by earlier I mean M3 stars, and then we exclude sources with high extinction and also exclude close binaries, which might affect their large-scale disk structure. So the main result is summarized in this figure. So this is the gallery of our 32 disks at 1.3 millimeter. And they are displayed in order of millimeter fluxes. So we have like brighter sources in the top panel and fainter ones in the bottom panel. So as you can see very clearly that it's similar to the D-sharp results. We have many disks which have prominent substructures, as you can tell there, but they emerge from both the brighter sample and also the fainter ones. In the meantime, we have many disks which looks very featureless and compact, and some of them indeed resides in multiple stellar systems, but at separation about 1 to 2 arcsecond. So let's first look at the set of disks with substructures identified. So our blind search reveals that the most common type of substructure you might expect is those axisymmetric gaps and rings. Any spiral arms or high contrast azimuthal variations should be rare. Those substructures have been emerged from systems across the full range of spectral type covered in our sample, that is from A-type stars to M3 stars. So we have performed parametric fitting to the visibility, trying to understand the emission morphology of those disks. So here I show the model results of the 1D radial profile. So as you can see that there's a wide diversity in, for example, in the numbers of substructures that each disk can host, and also in terms of their locations, weights, and contrasts. So the substructures can identified and down to our resolution limit, about 10 AU and outward to 100 AU. So those properties are very important parameters for us to understand what is causing them. So it has been proposed that ice lines can be across the ice lines, dark screens will change their properties, so will appear as bright and dark in bright dark ring emissions. And then this can be easily tested because we can calculate where the expected ice line would be. So we can assume that the disk midpoint temperature mostly scales with stellar luminosity. Then our comparison shows that not all gaps or rings have their corresponding ice line location. So this result tells us that the ice lines cannot be the universal mechanism in causing all those substructures. There must be something else working play together or solely by other mechanism to work. Of course, planet interaction would be the most exciting explanation. So it is very easy to imagine that if you have a more massive planet, it will create a wider and deeper gap. So therefore, we can, using those gap ring properties we derived from the observations, try to infer what kind of planets might be responsible for the gap opening. So we did a simple calculation by relating the gap ring weights to a few times the planet Hill radius, and we found that in most cases, low mass planets like Saturn mass can explain our observed gaps. If we put all of those measurements together on this disk mass, on this orbital distance and planet mass diagram, you can see that those gap-inferred young planets are mostly occupied in a distinct region compared to other mutual exoplanets discovered. I should note that this is the location of PD70b on this diagram. That means that most of our planets are below the current detection limit. Although this planet mass estimate is very brief, but I think we are currently unsuccessful in detecting those planets means that they must be low mass. A question we should ask ourselves is that, does every gap rings are caused by planets? I guess the answer may be no, but given that we are unable to directly detecting them currently, we need multiple indirect piece of evidence to confirm there might be a planet there. And so,
excuse me, we have a question from the chat from Bradley. So he asks, are all these bumps statistically significant?
That was also for several slides ago.
Oh yeah, I can get back there if you want. So, which statistics are you mean this part or?
The one you just flip by. That yes.
Which part of the statistics you are referring to?
Well, I mean, so there's some very, like MWC 480, for instance, there's at 100. So I should take all of these as real, or the one on the right-hand side, there's a sort of almost.
Oh, you mean some features are very shallow and some features are very deep, right? Yeah. So I think this is another problem. You can imagine that the shallow features are somehow in the inner part of the disk. So if the ring gaps are very narrow, there could be our 1080 resolution cannot resolve it very well. So there's a resolution limit that's applied in all those measurements. So if you can observe this disk at 280 resolution, they might become very deep in the radio profile. Yeah. So it's currently hard to constrain, but I think at our resolution, we can only tell is that, okay, there's a wide range of those contrast of the gap rings. Yeah. So I guess I can keep going. Yeah. So for example, in a planet disk interaction scenario, a pressure bump can be created outside the planet orbit. So around this pressure bump, different sizes of grains will accumulate there. And so they will form like those kind of ring features. So a very simple consequence is that if you observe the system at different wavelengths that tracing grains of different sizes, you should expect to see very similar morphology and similar sizes. More importantly, this trapping effect would be more pronounced for larger grains. So that in that case, the ring structure at the longer wavelengths will become much narrower because they are tracing the larger grains. So those scenarios can be tested by multi-wavelengths observations. So we have conducted some follow-up observations with ALMA band 3 at 3 millimeter for a few disks, and that allowed us to achieve comparable resolution compared to our initial 1.3 millimeter image. This pilot survey only used the 3 disks, so we included disks with around different types of stars and have different disk millimeter luminosity. So our results show that those disks have very similar morphology and they have similar sizes. And in some cases, we do find a narrow ring at a longer wavelengths. So all those results are consistent with dust trapping at play, which might be caused by embedded planets. And so if we have measurements at multiple wavelengths, we can also try to constrain dust grain properties there. And so we have did this radio profile for the opacity and spectral index in the disk. We can see that across the high density peak, the ring location as indicated by the dashed line here, we see a local minimum of those index. So the spectral index is a value that usually used to test the maximum grain sizes in the system. A lower value will often indicate the presence of larger grains. So this tells us that across the high density dust ring location, there might be enhanced grain growth occur, which is which might make this location as the optimal location to converting pebbles into planetesimals and forming new planets. So all those analysis is based on assumption that the dust emission has to be optically thin. So our calculations show that the optical depths in our rings in some cases can be marginally optically thick. So the solution towards this is very easy. You can just move to the longer wavelengths, but that's not very easy. So we are making some progress towards moving to longer wavelengths. So we have requested for VLA time for this single ring system, MWC480. So in order to detect this faint ring, which means that we have to reach a sensitivity of 1 micron Jansky per beam, because the ring at the 9 millimeter would be more than 100 times fainter, and this will requires like 50 hours of VLA time. I was really thrilled, also surprised that VLA allows me to do so. And so I'm showing here a very preliminary results. So using the ALMA data of 35 hours time, we found that this is the new image at 9 millimeter for MWC480. If you can look very carefully, you might find this faint ring in outer part. This ring only appears after I did self-calibration. So it's really a pain to reduce this massive data set. And we just got the B-array data last month. So we'll see how adding the two array data together, how the final image will be looking like. And I hope that we can better constrain the green properties in the system and also constrain the dust trap mechanism at play there. So that being said, we really need NGVLA for this kind of research to work, because NGVLA may work in a few hours compared to 50 hours integration time. Okay, so I have discussed the 12 disks we find in our sample, which show substructures, but there are remaining 20 systems which are kind of smooth. I call them smooth because we don't find substructures on larger scale. Those smooth disks also include eight systems that are in wide binaries. So by comparing the properties of the samples, we found that the emergence of substructures do not have a strong dependence on their stellar mass or disk millimeter luminosity. So it's interesting that those smooth disks, they also appear in disks around the same type of stars as those substructure disks. So whether those systems will have smaller scale substructures is still unknown. I have some observations being conducted at 20 millisecond. I hope that data set will help answer that question if those compact ones do show smaller scale substructures. But apparently the emergence of substructure depending on their scales. So you can see that this plot shows the x-axis, the size of a disk, and y-axis, the millimeter luminosity. So substructure is primarily found in those larger disks. So we may draw a conclusion that larger disks will always host substructures. Is that true or not? I think we need a big data to answer that question. So I see there's another question, but I couldn't.
Yeah, so could you show Shokong asks, could you show the residual because VLA has some beam artifacts?
Oh, okay, you mean, yeah, so this is like, I think we are still in the process of reducing the data because you can see this pattern, this might be a pattern residual. I haven't been able to crack them out fully. So yeah, but I think the ring might be real, even though there's some phase noise associated with the image there. Yeah. Did that answer your question? Sure.
Yeah, sure says thank you.
Yes, thank you.
Okay, so now I'm trying to move to our more complete view of the substructures in torus disks. So previously we only touched for 32 disks there. If you can So actually, there are like more than 100 targets in Taurus that have spectral type earlier than M3. And I have searched for in ALMA archive that we find there are 79 of them. They do have data available with resolution better than 0.2 arcsecond. So this new sample is now highlighted in this stellar mass and millimeter luminance diagram. So you can see that now this new sample can be very well representative of the whole population of Taurus disks around these types of stars. So the results I will be presenting soon are mostly done by my summer student, and Steve Darcy, who is an undergraduate from Massachusetts. So I think the image tells everything. So this is the millimeter image for the 79 disks in our new sample. As you can tell, now this new sample includes many close binaries, which are initially flagged out in our dedicated survey. So the images are showing the same scale, so you can see how relatively the distribution can be different from each other. So the panels are displayed from early type stars to late type stars. Those are the 3 A-type stars in Taurus. Everyone shows substructures. It's very striking to me is that if you're looking at stars around stars with similar spectral type, their dust morphology can be very diverse. So with this large sample, we are trying to analyze which disks can host the substructures. This time we are doing it differently. So previously we are trying to using parametric model fitting on the visibility, which is really time consuming. Now I'm using Frankenstein fitting that computes non-parametric models on the visibility data. It's super fast, and the tool was developed by Jeff Jennings. If you're interested, you could look at his work. So here I'm trying to mark out the systems and the orange curves showing the Frankenstein fitting result, and only for those systems which identify new substructures which were not originally reviewed from the image plan. Image plan curve was showing as the blue ones. So you can see that we do find a few new substructures, especially for T tau. So T tau is only spans 2.1 arcsecond. I was very surprised to see there's a very deep gap associated with T tau. There's also another paper recently. They using a different fitting method using our data. They do find this similar morphology. That this could be real. So in summarize that. We can see this is the size distribution for our sample. I categorize them by their appearance of substructures. So the orange histogram shows disks with substructures, and the blue hash diagram shows those without identified with our current data. So the median size in a sample is about 0.2 arcsecond. That means half of our sample do show substructures, and they preferentially coming from those larger extended disks. So I think this gives us confidence that we could conclude substructures in dust distribution are ubiquitous in larger disks. So those analysis is based on around early type stars. I want to highlight that the M-Dwarf systems are also very interesting. They are important planet hosts. But the problem is that disks around M-type stars are always much fainter and more compact. So if you want to characterize their disk structure, we do need very high resolution. So we have been trying this for many times, and finally we got some new data done with 30 millisecond resolution. So the first data released from this program was really interesting. So this system shows that dust emission are primarily confined into 2 narrow rings, and the inner disk is totally empty. It's really rare to see such extended disk around M4 type star. But however, this morphology or this size distribution is is also supporting our conclusion that a larger disk will always host the substructures regardless of their stellar type. Okay, so this sample also includes, I say that this sample also in these compact systems, many of them are coming from binary systems, as I just told you, because this new sample are including those systems we initially flagged in our survey. So using our initial Taurus data, Karim and Naro have compared the disk sizes among the sample. What he found is that systems in multiples are much compact than around single stars. Now in about half of our sample are actually in binary systems. We could do the similar analysis. So here in this white panel, I'm showing the disk millimeter luminosity compared to their sizes. So you can see clearly that those systems in binaries are much fainter. They are showing two distinct peaks, and they're also being much compact. But this comparison is not that distinct. I think it's mostly because we have some targets which are very bright but also very compact. So that, as I told you, those targets might be suffer from efficient radial drift in the original outer disk, that everything has been accumulated in a confined region, and this can be tested by some gas observation to explore how the initial size would be looking like. That would be also interesting to see in the future. So the sample I discussed here for those binaries have separations of 30 to 600 AU. So at this separation, each star can host its own disk. That is called those kind of circumstellar disks. While in some rare cases, you could also have a disk that's surrounding both stars, which we call as circumbinary disks. Those circumbinary disks, as showing a few examples in this diagram, they could be as bright as disks around single stars and also have similar sizes, but their structures can be very different due to the binary interaction process. You can imagine what they might happen there. So here I'm showing a few examples of how having a binary in the system can causing a different appearing of the structure in the disk. So we often see inner cavities in the disk and also spiral arms. In some cases, shadows that is caused by the misalignment in the inner and outer disk. And so to correctly interpret all those features and to understand the details of binary disk interaction, we do need information from the binary orbit. And such information requires a long-term monitoring and is rarely obtained. So I would like to show one interesting example that we're able to constrain both the binary orbit and also the disk structures. So V892 Tau is a closed binary, which is only separated by 7 AU. It is thought to have two A-type stars in the center. And then in the VOA data that we obtained from the archive, we found that there is very bright free emission associated with as 2-point source that could trace the two star location. And then if you compare the two epochs of the star location, there is clear binary motion. So we could use this new estimate, the new constraints on astrometric measure as a position to obtain a better constraint on their binary orbit. Also, I note that there is another low mass companion at 4 arcseconds away to the northeast of the system. So these two stars also host a massive circumstellar disk. So here I'm showing the disk image from the mid-infrared, millimeter and centimeter. So you can always see this inner cavity associated in the system. In some cases, we do see some subtle azimuthal variation in the disk. The CO emission is also detected, but the CO disk is appearing on a much larger scale. And so I will first try to give an idea of how we constrain the star properties and also the orbit, and then see how those can explain the disk structures we observed in the whole system. So the total stellar mass, it is an important parameter for to constrain the binary orbit. However, if you have two stars very close in the center, their mass constraint from those evolution checks can be totally wrong. Alternatively, we could use the gas motion in the disk to constrain the total dynamic mass of the system. So here shows the ALMA observation of CO gas in the system. We can see that the CO emission coming from a wide range of velocity, and the emission pattern is very consistent with predominantly Kepler notation. So we can simply model this emission. We model the CO brightness distribution in each channel and assuming a Kepler rotating disk. And then our estimate shows that the total stellar mass would be 6 solar mass. This is consistent with the view that the system have 2 A-type stars. This model also provides good estimate on the geometry of the disk in terms of inclination angle and position angle that we will use later. So with this well-constrained stellar mass and also Gaia distance we're using the Gaia, the DS3 distance, now we are able to constrain a better orbit by also including our VOA measurement of the astrometric points. If you still remember that, we have like 2 distinct points for the VOA image. So this is I'm showing here some likely orbits for the system. Our preferred orbit is mildly eccentric with eccentricity about 0.3. And the system has a period of about 8 years with inclination angle of 60 degrees. This inclination angle is very similar to the disk inclination angle that we just derived from the dynamic mass modeling. So, however, we lack of radial velocity information for the system because of high extinction around. In that way, we couldn't know exactly what is the true orientation of the orbit. Therefore, it leaves us 2 possibilities of the position angle in the system that we will refer to later. So discuss about the stars. Now let's look at the disk. So the dust disk contains an inner cavity. This cavity is observed in both the 1.3 millimeter and also 9 millimeter from VOA. If you're looking at this radial profile, you can see that this ring location has been well detected in both wavelengths around 0.2 arcsecond. This peak location about 0.2 arcsecond is roughly about 4 times of the binary separation. Also, if we can inspecting the VOA data very carefully, because in this case, we're able to pinpoint the center of the stellar mass, we found that this cavity is kind of likely eccentric, but a confirmation of the eccentricity will require more high quality data because you can see it's very low signal ratio in the VOA image here. So normally, if we have a cavity ring system, we try to model it with a Gaussian profile. But in this case, we are trying to relax the parameters. We set the weights of the ring inside and outside the peak as free parameter. This is to account for the possibility that the inner disk might be severely truncated by the binary. So indeed, our fitting prefers a asymmetric ring that the outer weights is about twice of the inner weights. So this kind of asymmetric ring structure describes our data reasonably well, but we do see some pattern residuals in the map. This residual suggests that there might be some subtle azimuthal variations that we already see from mid-infrared image. So there are some perturbations that imposed on the dust disk. This inner cavity is also detected in the CO data. So we have detected all 3 CO lines. and their radial profile is plotted on the right-hand side. So you can see that the inner cavity location is not well constrained. This is because the central channels are strongly affected by foreground cloud emission. So we're not able to really identify the inner cavity of the gas disk. That is a parameter most important for the truncation theory. But somehow we can put upper limit is about like less than 3 times of the inner cavity separation. Also, this CO gas disk extends to 200 AU. If you can look carefully on the moment zero map, you can see some very interesting features in the outer disk. Those non-axiometric features and also the size it could be the imprints of interaction between this circumbinary disk with the 4 arcsecond companion to the northeast. But that connection has to be verified with more sensitive data set to see if there's a bridge emission connecting the two systems together. So with CO data, we're also able to constrain the thermal structure of the disk. Now in this plot shows the brightness temperature image of the disk, which is also known as moment 8 maps. So it's very striking to see the wide, very large thermal structure variation across the disk. This profile gives a closer look. So I have extracted radial profile from each side disk, and this red curve is extracted from only the redshifted disk side, and the blue curve is extracted from the other opposite disk side. So around 100 AU, the redshift disk side appears much warmer, have a warmer plateau in the distribution, and then it drops quickly in outer disk. This quicker drop, therefore, introduce an inversion of the temperature structure in the outer disk. As you can see that around 200 AU, the outer disk on the blue shift disk side is much warmer. So this kind of temperature inversion can be explained by some simple models. So we are using so in this case, we propose that it could be that the disk has a mild disk warp. So you can imagine that the inner part of the redshift disk side is slightly puffed up. So it receives more stellar light and becomes much warmer. Meanwhile, the outer disk of the blue shift disk side also directly exposed to stellar radiation and then becomes much warmer than the opposite side at the same radius. So this kind of morphology can be explained by this mild disk warping scenario. The disk warps have been well predicted in binary disk interaction models. So for example, this is a very pronounced case. In this scenario, the simulation show that the disk can be break into distinct pieces. Inner part, outer part have total different orientation. And those features can be easily produced if the binary plane and the disk plane have some initial misalignment. So that requires us to assess if our system do have those kind of misalignment. This misalignment can be described by a parameter of mutual inclination. That requires we constrain the geometry of both disk plane and the binary plane. As I just said, we're not able to constrain the true orientation of the binary because we lack radial velocity information. So this provides 2 possible solutions. In the first solution, we found that the mutual inclination angle is very low, which is close to a coplanar case. However, in the second case, the two planes are highly misaligned. So based on the series, 2 initially misaligned systems can evolve to either a coplanar case that is about 0 degree or a polar case at about 90 degree. And this final fit will depending on their initial misalignment. So, and the thing is that this realignment is working on a timescale, it's working on dynamical timescale, which is much shorter than the disk viscous evolution timescale. So given our system age about a few million years old, I think we would prefer the first solution to be the case, that if the two systems are initially misaligned with degree less than 660 degree, then the two plane are now slightly evolving to a coplanar case. So putting all this together, I think the whole system can be explained by those simple scenario that there's an eccentric orbit, eccentric binary in the center, which is initially misaligned with the circumbinary disk. And in the process of the realignment, they produce the disk warps that we see. Also, the size of a disk and this dust ring morphology is very consistent with the truncation models we found what expected. Okay, so to summarize what I have discussed, I first talk about substructure view in Taurus systems. We found that substructures should be ubiquitous in larger systems across different spectral type. Then we found that those features, those substructures, can be explained by low-mass planets. And also around this ring location, there is enhanced green growth occurs, that they might be the optimal location for forming new planets in the disk. Of course, the sample not only find substructure disks, we also found many systems that are very compact, and some of them are really shaped by the binary disk interaction. And finally, I hope that our study of the binary system V892 Tau can provide a better constraint on the binary disk interaction models, and also help the series to better constrain their models. Also, this kind of feature occurs in circumbinary disks, can be borrowed, or same physics can happen in plane disk interaction, but the features might be shallower to detect. But I think with better data in the future, we're able to pin down all those features associated with plane disk interaction. Yeah, that's what I'm going to discuss. I'm happy to take any questions you might have.
Okay, thank you, Feng. So if you have any question, please raise your hand. Or you could write in the chat.
I somehow mistakenly closed my screen share.
Okay, so I don't know which one was first, Ilaria and Caitlin. First, let's Ilaria.
Okay. Hi, thank you very much for the nice talk. The extended Taurus sample is really impressive, the one you have here. I was wondering, is there any preferred ratio between the location of the structure and the disk size, or everything is possible down to the resolution you have? Thank you.
Yeah, I haven't did that exercise, but I would prefer your second suggestion. I think every location is possible, given the resolution limit we have. Yeah. But the thing is that many disks only observed at 0.1 to 0.2 arcsecond, so it's very uncertain. We're still missing many substructures in these compact systems.
Okay, thank you. Caitlin?
Hi, thanks again for a really nice talk. I have two quick questions. First, can you go back to the slide where you were talking about fitting the V892 Tau disk? I just wanted to understand, I think that's the right one there. You got to click on. Not the orbit fit, the disk structure.
Okay, so you mean the last structure?
Yeah, okay, so yeah, this slide, yes. So I was just a little confused because the text at the top of the slide said model Gaussian ring plus point source inside the cavity.
Yes.
But I wouldn't think that you'd have a point source in the center of the cavity if there's a binary separated by 7 AUs. So
yeah, so I should make clarification here. So this is because I only use one point source, because you can see the beam is very large. So the binary separation is, the two stars are well within one beam. That's why I'm using only one point source to account for that possible non-thermal emission associated with the star that we see from the VLA data there.
I see, but do the residuals suggest that perhaps even given the size of the binary relative to that beam, that the single point source is not, I mean, should I take the fact that the residuals have that strong, that very specific structure to mean that there is a signal that's not consistent with being a uniform point source inside the cavity, or is that overinterpreting it?
So we also did exercise by free, so we add a point source, but we allow that to move away from the cavity center. And then that can result in off-center peak of the point source, which means that the star that are at a different location to the cavity center, that means it's kind of eccentric cavity there. But we're not sure because the beam is really large. It's comparable to the cavity size. So.
Okay. And then my second question was about, it looks like slide 33, the one where you were talking about the mutual alignment. Again, this is just a quick clarification. You mentioned that the realignment, you can either align to basically coplanar or polar.
Yeah.
But am I missing? I mean, the right panel where you have that one, I mean, that's not polar, right? That's substantially retrograde.
So that's why I'm excluding that scenario. I would prefer this first scenario.
I see. Sorry. I thought you were saying you were preferring the aligned scenario to the polar scenario. And I was like, but there isn't a polar option. It's straight up retrograde.
Yes.
And you can't rule that one out based on the gas kinematics because of this PA uncertainty.
It's a PA on the binary. We cannot consider it. Yes. Okay. But the thing is that I do know the exact orbit of the system because Adam Klaus has a full orbit, but I couldn't use that information. But still, they don't have radial velocity information. They only have a full orbit.
I see. So you can't, in principle, do the direction. So
yes.
Yeah.
Which is unfortunate.
Anyways, it was great. Really nice talk. So thanks.
Okay, Andrea.
Hey, Feng. Hi. Thank you. Beautiful data and great work. As you know, I got very interested in V892 Tau recently, and maybe this builds a little bit on what Caitlin was asking. Can you go back to the slide where you had the VLA data too?
This one?
Yeah, this one. Yeah, exactly. So the VLA data peaks at the very center. So the 9mm data has a peak at the center where there is the gap in the 1mm data.
Oh yeah. So this peak in the center are from the stars as I used. So this is almost free emission.
Okay.
So that's why I'm using that to do the orbit fit because I have a new constraint on astrometric position. Okay,
great. Yeah, that was the question. I was wondering whether there was the inner disk that had very different dust properties. Or thank you.
Yeah.
Okay, any other question? Actually, I have a question. So I'm curious about the dust disk sizes. I tend to be more compact than gas disks. And for Taurus, if you have, I don't know if you have addressed it, good idea about what factor the gas disks may be bigger.
Oh yeah, so I have a recent work I haven't published, so trying to measure the size of the gas disk compared to the dust disk size. Mm-hmm. So in principle, it's a factor of 3. That's a median value, but it has widespread. It can go from like 1-ish to 7. So it's an extreme case like geo tau in our sample, this one. So the gas disk goes to 1000 AU. That's a factor of 7 larger than the continuum disk. We don't know why that become monster in that sample, but in most cases, it's a factor of 3. Yeah.
Oh, so it's not related to the spectral type or central disk?
No, there's no correlation on that ratio for any stellar disk properties. So it's very mysterious. Yeah.
All right, thank you. Yeah, I'm curious about that even for instance, like Orion's disk, whether the gas disk size to dust disk size ratio would vary based depending on the environment. So thank you.
Yeah, I think the key question is that the dust size is really controlled by the last pressure bump you built in the disk. Mm-hmm. So it's irrelevant of their initial conditions anymore. that ratio can vary a lot. Yeah.
Okay, so last call for any question. All right, then let's you can turn video on, and let's thank Feng for beautiful talk.
Thank you guys for joining with me today.